Yay!
Yay! Okay, one more kind of interesting problem is we can kind of treat the case of a yo-yo. So now, instead of a stationary sort of a pulley being spun up, now let's take, it's sort of the reverse case, right? Let's take something that's like a hoop, and let's wind a string around it and then release the hoop. And so let's see, after this thing falls, let's say 75 centimeters, how fast is it moving? Once the whole hoop falls down, we're assuming that the mass of the string is negligible. So we don't have to worry about that, right? Because as it unwinds, you get less and less of the string on the hoop. Let's not worry about that. So as this thing falls, it's going to be spinning, right? So let's see how fast it's going to be going after it drops 75 centimeters, and it's unwinding the whole time. Okay, so the easiest way to do this is, again, energy methods. So initially, it's 75 centimeters above the final position, right? 0.75 meters. So let's call that h. That's the height. And so initially, it's all potential energy. So mgh is the initial energy. And then finally, when it reaches the bottom, what's going to happen is that it's all kinetic energy, right? So it's moving downwards. So I'm going to have a 1/2 mv squared. And it's also rotating, right? It's spun up. So I'm going to have plus a 1/2 I omega squared. So I got my kinetic energy of the center of mass. Oops. I meant to call that kinetic energy of the center of mass. And then I got the kinetic energy of rotation. I add them together to get the total kinetic energy. Cool. All right, so let's do that. So I got 1/2 mv squared plus 1/2. What is I? What's I for a hoop? That's just going to be mr squared for a hoop. And if it unwinds without slipping, omega squared is just going to be v over r squared. So look what happens. This gets really easy. The r's go away. That's neat. So I have 1/2 mv squared plus 1/2 mv squared. Those terms just add together. So I just get mv squared. On the left-hand side, I had mgh. So the mass doesn't even matter. So that means that the speed of this thing is just going to be square root of gh. So if you put the numbers in, h is 0.75 meters. What I got was 2.71 meters per second. Very cool. If it had free fallen, right? Oops. Free fall is root 2gh. That's how fast something falls if you just drop it from a height h. And that would have been, what was that? 3.84 meters per second. Okay, so what you can see is that the yo-yo is going slower than you expect after it falls from a height h. But that makes sense, right? Because some of that speed, some of that energy has gone into rotating the yo-yo as opposed to just falling. So it does sort of all make sense. Neat.